I'd like to go back to warm-up exercise 3, but this time describe the procedure from a more abstract perspective. And the advantage of doing so is that the abstract description of the procedure will be exactly the same to what we're going to do when we prove the Banach-Tarski theorem for real. So what I'm going to do is I'm going to start by talking about Cayley paths without worrying about how they are implemented geometrically. So I'm just going to think of the Cayley graph as a collection of paths. So we have the empty path, which starts at the center and goes nowhere. And then we have 4 one-step paths, right, left, up, down. And then we have a bunch of 2-step paths, right, right. There's, of course, no right, left. That would be forbidden. But we do have right up, right down, left, left, and so forth. And then we have some 3-step paths, and so forth. So this is our Cayley graph from an abstract perspective. Now, remember how we implemented it geometrically. So what we did is we decided to think of each of these steps as movements on a plane. So right is a right movement on a plane, up is an up movement on a plane, and so forth. And our geometrical implementation assumed also that steps get shorter and shorter. So for example, when we go right, right, we first advance a half unit and then a quarter unit. So this is the graph, and that's the geometrical interpretation that we're giving the graph. Remember what the next thing we did was. We divided the graph, ignoring the center, into quadrants. So one way to think about that is that we took the graph and we decomposed it into right, left, up, down, again, ignoring the center, where each of these is a subset of these paths. So right, for example, is the subset of C that consists of all paths that have right as their first step. So we get that path and that path and that path, and then a number of 3-step paths and so forth. So abstractly, we have a set of paths which we divide into 4 subsets. The geometrical implementation of this lives on a plane. We have the set of all paths, and we divide them into 4 quadrants. Now, the next thing we did was notice that the right quadrant was just like the down, right, and up quadrants taken together, except that it's reduced in size and a little bit to the left. So if we expand it in size and translate it to the left a little bit, we get something that's equivalent to down, right, and up taken together. So there it is again. So let me tell you, in this abstract setting, what it means to go from the original right quadrant to the expanded and translated version of the right quadrant that you see there. So what we do is we go from this set R to a set R arrow, which is a result of taking each path in R and removing the first step. So by removing the first step in that path, we get the empty path. By removing the first step in each of these, we get up, down, right. By removing the first step from each of those, we get right, right, right up, and so forth. And notice how our arrow, as we defined it here, on our geometrical interpretation, really does correspond to all of that area, because we have the empty path right there, and then we have up, down, and right, and then we have right, right, right up, right down, and so forth. Everything that's colored in red there will correspond to a path in here.